Hello, my name is Luke, and this is the first of a series of screencasts about the relationship between category theory and programming. As a programming language, I prefer to use Scala, more precisely Scala 3.0, for various reasons, which I will explain later. Scala comes with a build tool called SBT, so I will use that one as well. And nowadays there is a support for Visual Studio as well, and the simplest way to start Visual Studio from within SBT is as follows: SBT launch IDE. Okay, this will do a lot of stuff, and eventually you will get a screen. This first screencast is an introduction to my library, which is called the Program Description Based Programming Library. Here's the logo. And so my first package is PDB introduction. For those who are interested, here is the build SBT file with the organization, the version, the .dotty version. It's the latest .dotty version, which is feature complete. And I will work with subprojects, and my first subproject is indeed introduction. So many more of those will follow, but that's for the next sessions. So let's go back to the introduction thing, and let's start SBT here. The running example is the well-known Factorial Example, which you see here, at least the first version of that Factorial Example. By the way, now I see that I have to put some things in comment. Don't worry about that, I will copy paste from those by need. So I have my first version, and that first version defines factorial as a function from begins to begins. It has a parameter n. If the parameter n is 0, the result is 1. If not, then I recursively call factorial with argument n minus 0 multiplied by n, and then yield the result obtained by multiplying both. Okay, nothing special about this. It's certainly not the best possible factorial definition you can think of, but that's not the point of this introduction. The point of this introduction is that I will transform this factorial to two versions. One version that is extremely expression oriented. It will eventually expose an evaluation strategy of expressions. Another version is more function oriented, and it will expose the essential function combinators to construct programs with. More about that later. But let's first run it. Maybe I should do it like this. Row. Yes, sorry, that's the normal one. I should type in introduction on, because like I mentioned here, I work with subprojects, so I should do it this way. Sorry for that. Here we go. All right. Good. Let's go to the next version, which is this one. Here we go. And change this one accordingly. I didn't do a lot of things. I just made explicit that functions are objects that have a method or operator, if you like, apply, that allows them to be applied to arguments, in this case n-1. It shouldn't make a lot of a difference, so let's just run that one again, and it still works. Now let's go for application everywhere. This is an expression which basically is applying a function is0 to n, a Boolean valued function. This is basically an expression which applies a constant function 1 to n, and so on. And so let's let's uncomment, a few things here, and go to version 3. I'll come back to the things I've commented out in a minute. And here's version 3. And I'll change that accordingly. So, like I said, I need a function, a Boolean valued big integer function is 0. This one is a generic one that always returns 1. This is the one that subtracts 1. Then I have this little type alias so that I can use type expressions like this. Notice that multiply indeed is a function with 2 arguments, or with an argument tuple or a product argument, if you like, which multiplies the 2 elements of the product. And let's see what happens. But before doing that, let's look at our refactored or our transformed factorial. And indeed, I'm applying everywhere now. I'm applying is0 to n. I'm applying 1 to n. I'm applying subtract 1 to n. Then I'm applying factorial to the results. And then I'm applying multiply to that tuple containing the original parameter and the result of evaluating this one, right? Let's run it. Still seems to work. Now we could go further with this apply, but I prefer to do the opposite. Just like functions can be applied to arguments, arguments can also be bound to functions, and it's easy to encode that in the following way. Given, and let me correct me this one, any z of type z, in fact it is a generic binding operator, so I will bind any z of type z to a function z to y of type c to y. Notice that this one is a by name parameter, because if the evaluation of z, which could be an expression, fails, then it is of no use to continue. And also notice that I use kind of funny, what I call typeful names, which hopefully will turn out to be illustrative if we are dealing with complex expressions. But hey, it's very simple. If I just bind this z to this z to y, it's the same as applying z to y to z, right? Good, then we can go for our next version. And run it. Okay. What's next? Remember that we were going to expose the evaluation strategy of expressions, and well, let's go for a kind of bottom-up strategy. For pure expressions like the ones we use here, the strategy doesn't really matter. The result is independent of the strategy that has been used. But, you know, this is probably the first thing you are going to do, evaluate it. And what we first will do is we'll introduce local values capturing that evaluation strategy. And we will also make explicit that we are evaluating expressions yielding a result. So remember, we have already used binding, a little bit of a funny operation, and now we are also going to introduce our next interesting thing, yielding a result, but that's basically just the identity function for the moment for functions. So let's go for number 5. So remember, we are probably first going to evaluate the result of binding n to a 0. Introduce, besides the already available parameter n, a local value b. Then we continue with our code. So 2 branches. If b holds, then we are evaluating the result of binding n to 1. Bind it to a new value p, and then just the result of my factorial is p. Okay, remember, p result was just the identity. Same for the case where b is not true. First I have to subtract 1 from n, evaluate it, bind it to q, bind q to factorial, evaluate it, bind it to r. Now we have both n, our original parameter, and our local value r at our disposal. We double them, bind them to multiply, have our new local value s, and the result is s. Let's run it. Okay, so the takeaway is that we have introduced those extra local values, which together with our original parameter enable us to make the evaluation strategy a little bit more explicit. But here's the point. We're going to immediately go back to version 6 . And the main takeaway from this session as far as expressions is concerned is that the introduction of those local values is equivalent with the introduction of local parameters. You don't see any vals anymore, but you see a lot of nesting. And within those nested scopes, you will see the introduction of new parameters. For the rest, it's essentially the same code. Okay, so you bind n to 0, to the Boolean function is 0, returning a Boolean value b. Then you continue, if b, you bind n to the constant function 1, bind it to the nested parameter p, and that's your result. The other one goes more or less the same way, a little bit more complex, but it's the same thing. So for a moment, for example, at this location, the parameters that are in scope, so to speak, are N, B, Q, R, and S. They're all available, but I only need S. Here I only needed N and R. But you see, N comes from the outer scope, R comes from an inner scope. So basically you're constructing more and more nested parameters, or if you like, local values. Let's run it, and it also gives the same result. Okay, let's now be a little bit more verbose. I'm not saying that you have to program the way I'm doing it now, but just to give you some idea about how this refactoring exposes the evaluation of expressions. I've renamed the result to evaluate the result of. Remember, it was the identity, or you yield result in the at the end eventually, which was also the entity. And I also renamed the operator symbol to bound to, where it reads better as bound to, and binded to, where it reads better as and binded to. But for the rest, it's exactly the same. I still have to change this one here. So you can almost read this from left to right like you would read a book. Evaluate the result of n bound to is 0 and bind it to b. If b, evaluate the result of n bound to 1 and bind it to p and yield the result p, because basically that's the end of one branch. And similarly, evaluate the result of n bound to subtract 1 and bind it to q. Evaluate the result of q bound to factorial and bind it to r. Incidentally, r stands for the recursive usage of factorial. Evaluate the result of this tuple nr bound to multiply, bind it to s, and yield the result s. So, to summarize, actually, excuse me, here it is. I'm going to finish with this version, version 8, which is a little bit less verbose, but also completely equivalent. I'm going back to those, well, you know, I introduced those expressions like n bound to is 0, but for those, let's say, atomic functions, we might as well go back to the original notation. That's what I do here. So read it as the result of evaluating n is 0, bind it to b. If b, then the final result is 1. Otherwise, evaluate the result of subtracting 1 from n, bind it to q, then evaluate the result of factorial q, bind it to r, evaluate the result of this product expression, bind it to s, and result s. It's very operational. It's really like exposing how these expressions are evaluated. Oh, let's, I skipped 7, but believe me, that one works as well. Let's run it. And here we go. This finishes our first journey about evaluating expressions. In the categorical sense, this will correspond to executing computations. And computations, for those who like the words, are monads. And the essence of the monads, well, are those two things: binding and results. So let's move along and let's continue with the second transformation, which will be more like a functional transformation. And let's start with version 9, which is again the starting version, but with those, because we are going to work functionally, with those auxiliary functions used. So yes, by factorial, if n is given, we are going to do the if then else. If n is 0, it's 1 of n, otherwise it's multiply of n and a factorial of subtract 1 of n. So let's concentrate on this expression. You recognize the application of a function to an argument, and then another application that has been applied to the result of the first expression, the first function application expression. We are going to introduce our first function operator, which is function composition, maybe more precisely sequential function composition, which is the following. Given a z to y, if I can transform a z to a y, and a y to x, if I can transform a y to an x with the appropriate types. Again, this is a by name one. Then most probably I'll also be able to transform a z to an x by composing both, which is exactly what has been written here. This leads us to version number 10. Which is already a little bit more uniform than version number 9, because you see here I'm applying something to n, here I'm applying something to n, and here I'm applying something to n. But I still have this multiply thing, and so we have to find some way of dealing with tuples, with functions that have tuple arguments. And how are we going to do that? Well, by using tupling, or more precisely, or said it in another way, by using products, or maybe in yet another way by using construction, or the initialization of new constructs. How do I do that? Well, I need two things here. Certainly the first one. If I can construct a y from a z, and if I can construct an x from a z, then I can construct both a y and an x from z. Notice it's a little bit biased. We'll come back to that later. So it's biased towards the first one, because the second one doesn't necessarily need to be used. And how do I do that? A little bit similar to the composition here. I'll simply tuple both results. Later on, I also need this. No, I think I immediately need this z to z as well, which is just the identity. It's doing nothing. And let's see how we can transform how our factorial to the next version. Look how cool. I'm applying some expression, some function expression to n. I'm applying some function expression to n, and now I'm applying again some function expression to n which is this one. Hey, but then I also multiply, so I can use sequential composition again and do that immediately, which is my version number 12. So you see the difference between both is that I'm now using the composition again and I'm applying this composition to n. Okay, let's see if it still works. Cool. But let's face it, this might be a nice expression for those who are mathematically inclined, but for normal programmers it's maybe a little bit too abstract or too, I don't know, mathematically oriented. And here's where Scala shines. Scala will enable us to drastically simplify, or simplify maybe not, because it's not about complexity, but drastically make this expression more elegant. Scala stands for scalable language, and we can define our own language constructs as library constructs. How we do it, I will come back to that later, but let's look at the next version. Once we enabled this, don't look at that code for the moment, it's not important. But here's our next version. There is here a nested let construct, which works as follows. Well, the idea of this expression is that I'm introducing a new local variable, the result of evaluating n-1, factorial of n-1, and this new local value is available with my original parameter and can be multiplied. So this replaces this thing here. Which sounds better, I think, for programmers. Also, those guys who know about Haskell know about the let-in construct of Haskell, so it's a little bit of a functional equivalent of the let-in construction of Haskell. It's really needed that we have this product, this construction thing, because with normal composition, remember, with normal composition you you have to face that your original argument, if I go from z to y and then from y to x, when you go from y to x, you don't have your z anymore. But here you still have it. In this let construct, I have my new local value, which is this intermediate, the result of evaluating this intermediate expression with n, but I still have my n, right? Remember, it's the same thing as here. If I apply this to n, I still have my n, but I also have this new local value, this expression which applied to n yields my extra local value. Okay, I told you that Scala can introduce new programming constructs at the library level. We just introduced our let-in. But what about the if-else? Well, we can do that as well, using more or less the same trick. For let-in we used products, remember. For if-else we are so here are the products. For if-else we are going to use sums. which you see here. So the sum of a z and a y is either a z or a y at the left side, a z at the right side, a y. Don't look at the other things, it's not so important for the moment. But what we can do is now go to version 14. And copy and paste that one. Oh, by the way, maybe let's first run number 13. Voila. So now this colored if-else became a back-quoted if-else, but for the rest it kind of looks the same. But look, here's my original parameter n, and I'm just applying this nested if-else let in thing, which is here. This is a big expression which I apply to n, so I might as well completely throw those two away, which means I can go to version 15, which is my last one here. Pure functional definition of factorial based upon factorial itself, a few auxiliary functions, this function combinator, sequential composition, the let-in construct which corresponds to the product combinator, and the if-else construct which corresponds to the condition operator. We also need the identity, but the identity was actually used in the definition of let-in, which you will see later. But let's run it. Cool, still works. So what does it mean? We have on the one hand transformed our factorial to one that exposes the essence of expression evaluation using the operator bind and the function result. And we've also translated it to an expression that only uses functions and function combinators. Function combinators are sequential composition, product, condition, and the identity. The rest of the sessions will deal with generalizations of this. Here we just worked with functions, but functions will be replaced by programs, and expressions will be replaced by computations. Expressions were evaluated, computations will be executed, and programs, well, you just run them. For those who are more inclined into the vocabulary of category theory, the computations will correspond to monads, and the basic operations there are result and bind. And the programs will correspond more or less to arrows, where the basic combinators are, well, the basic program is the identity program, and the basic combinators are sequential composition, product composition. Well, with those we actually have arrows, but we also add for conditional logic the condition construct. That's it.